Okay, then we can try to have a look at this task 26 about complex phasors. And we have given a time function for a voltage. So the voltage changes harmonically or according to a cosine function, or we could say sinusoidally. It does not really matter if it's a cosine or sine function. Some of these functions over time, how would we call this v with the head? This is the peak value, or it's the amplitude of this cosine function. What is this omega? Yeah, this is our angular frequency, we would say. So if it would be something that is mechanically rotating, then we would call it angular velocity. So for us, it's some angular frequency. And what is the phi? Phase. This is the phase shift, exactly. And so this cosinusoidal voltage function, harmonic voltage function, has an amplitude of 5 volt. So the value, the instantaneous value changes between minus 5 volt and plus 5 volt, because the amplitude range of this cosine function is from -1 to +1 with a certain angular frequency, and this has a phase shift of 60 degrees. And so now if we would try to draw this, let me take maybe black to draw a coordinate system with some time axis and with some amplitude axis, then yeah, this function might look like, always difficult to draw, but might look something like this. 60 degree phase shift. Now, could look something like this. Yeah, so the first peak usually of the cosine function would be at this axis, and now it's shifted 60 degrees into this direction because of the plus here. So yeah, if we think graphically about how this function look like, what does change if we change the amplitude? Yeah, so this scales, let's say, the function in the vertical direction, makes it smaller and larger. What does the omega change? This changes the horizontal scale of this function. So, but if we make omega larger, then let's say we compress the function together. Yeah, so it's a little bit the opposite way. If we make this larger, function grows larger in the vertical direction. If we make the omega larger, then we get more oscillations per time. And what does the phi change? We already discussed this, or I already said this. Yeah, so this not changes the scale, but let's say shifts the function left and right. And it's the same thing that if we increase phi, then we shift the function to the left. If we have a negative phi, then we shift it to the right. Okay, and so now we want to convert this time function or express this time function in the frequency domain as a complex phasor. And it shall be a stationary phasor. We can discuss this in a second what this means, and then we shall draw this phasor in the complex plane. And so now, as in most tasks, a question that could be asked is, why do we do this? What's the motivation to do so? What is the advantage of this complex phasors? Yeah, so we could express all our voltages and currents if we do network analysis with such functions. So alternating currents, alternating voltages, with harmonic functions, so AC circuits as we would call them. We could all express our time functions for current and voltage using these time functions there, but then we would really need to solve differential equations. So the idea is to express current and voltage as phasors and to express our circuit equations as also complex equations. And then we don't need to solve differential equations. We just need to solve usual algebraic equations, but they are complex then. That's maybe the disadvantage. But for this, we need to express this as a phasor. That's the idea why these phasors are super useful. This is what we will see in the next task that I can maybe spoiler here already in the task 27. Okay, and so, yeah, the idea of this phasor is that in this phasor we need to include this information of amplitude and phase, but not the angular frequency. Why don't we need the angular frequency in this phasor, or at least not in this stationary phasor? In some rotating phasor, it would be somehow included, but this is at the end also not very practical. In this stationary phasor, we just have amplitude and phase, but not angular frequency.
We look at it at t0,
so? Yeah, we look at it at t0. So if the time is 0, then the frequency also does not matter. That's one pretty good reason. And any second reason? The second reason is that the angular frequency will be the same each and everywhere in the circuit. If we look at the steady state solution that occurs. So think of a circuit like this one. So we have a current here and we have a current there and we have a current there. Okay, and in this case we have just one voltage, but we could have different voltages and different currents in a circuit, and each current, each voltage might have a different amplitude, might have a different phase. So we need to save them, let's say, individually, but the frequency will be each and everywhere the same. So the frequency has just one value for such a circuit. Okay, so the idea of this phasor now is, as said, we need to have one phasor that includes amplitude and phase. And all numbers that you usually calculate with in mathematics, they have just one value. If you have a natural number, if you have a real valued number, if you have, I don't know, a rational number, they all have just one value. But there's one type of numbers in mathematics that have two values at the same time, or that include two values in the same number. Complex numbers, yeah. And so the idea is, if we use a complex number for this phasor, then this one number at the same time includes amplitude and phase. And that's why it's a good idea to choose complex numbers for these phasors. So who has ever calculated with complex numbers? Okay, some, more or less, okay. So for this complex number, we usually write an uppercase letter and we draw maybe an underscore below it to denote this is a complex number. And the uppercase letter usually shows that this is some RMS value. Maybe in this case we just write a lowercase v and say, because nothing is written here, that this is some peak value phasor. We can discuss this in a second, but maybe this is simpler to start with. So this is our complex phasor. And now how do we write this as a complex phasor in this exponential form? We just take, super simple, we just take this amplitude and then we say E2j So Euler's constant to the power of the imaginary unit and this phase angle that we have. So that's it. This is this time function expressed as a complex phasor in the exponential form. Okay. So then there is some trigonometric form and there is some Cartesian form. So how does this trigonometric form look like? And how does the Cartesian form look like? Any ideas? So then we can discuss how could I rewrite the e to j phi.
Cosd plus j is
Yeah, so this is called Euler's identity, and this is the same as the cosine of phi plus the imaginary unit j and the sinus of this phi. And another comment to this imaginary unit, so this j is the square root of -1. And mathematicians would write I for this because it's the imaginary unit. But in electrical engineering, we already use I for the current, so it would totally confuse us. So we use J. And so in a tool like Octave, you could write I and you could write J, and they would both give you the same thing of one imaginary unit. One comment, if we are already talking about Octave and MATLAB and maybe Python in this case, the problem with I and J is if I set I to 2 and J to 3, because they are also usually numbering variables that you use in loops maybe. Yeah, and so now if I ask for I or if I ask for J, they don't have the value of this imaginary unit anymore. So it's always more robust to write one I or one J, because one I or one J will always map to the real imaginary unit. You cannot reset this. Okay, and so we could manipulate this equation and say I squared is -1, or j squared is -1, and the -1 could be also written as e to j 180 degree, and if you convert the 180 degree into radians, then it's p. So e to jp equals -1. This has nothing to do with that has something to do with electrical engineering, but this is a formula that mathematicians, let's say, totally freak out about, because it's a very short and very nice and simple formula that combines Euler's constant, the imaginary unit, p, yeah, as the circle number, and 1 or -1 as the neutral element of the usual multiplication. And so I think this is somehow called Euler's equation, if I'm not mistaken. Okay, so now we can use this Euler's identity here and rewrite our complex phasor from the exponential form into this trigonometric form. So we get 5 volts multiplied with cosine of 60 degree plus j sine of 60 degree. And yeah, so then we can just calculate this and combine this with each other, and then we get the real part of the Cartesian form. And if we take the 5 volt and multiply it with the sine function and the j, then we get the imaginary part of the Cartesian form. And yeah, I could just do this in Octave. So if we have 5 times cosine, and the cosine for degrees is, I think this is called cosd. This is a cosine function for the argument in degrees. So we can take 5 volt times the cosine of 60. Then we get 2.5, which perfectly makes sense. So the real part is 2.5 volt, and the imaginary part 5 times the sinus of 60 degrees is 4.33 volt. And yeah, if we think in a different way about this problem, how is the cosine function defined and how is the sine function usually defined? What does cosine mean? Or what would be one way to define a cosine function? If we have a right-angled triangle, so this is the longest side. Hypotenuse. So this is the hypotenuse. I will call this C, and this is one of the legs, and this is the other leg, and so this is the right angle that we have there, and let's call this angle alpha, and this side A and this side B. Yeah, so then A is the same as, it's corresponding to the sine function, so this is sine alpha times C, and the B is cosine alpha times C. And yeah, so one problem with this definition of the sine and cosine function in this right-angled triangle is that the right-angled triangle cannot have an alpha angle that is larger than, or that is 90 degree or larger. So one idea would be, let's take black for a second, so to extend this triangle, let's say, in a way that we say this is some imaginary axis, this is some real value axis, and then we have already drawn the complex plane, and that we have a unit circle, and this would be some triangle inside our unit circle. And so now we can have this hypotenuse as a phasor that is rotating around here. And so the phi angle or the alpha angle is always the angle from in the counterclockwise direction counted from the positive real axis. And so then always this side is the cosine of this angle, and if it's a unit circle, then the hypotenuse is 1. Yeah, so this leg is always the cosine. This is the real part of the complex number, and this side, or this length here, is associated with the sine of this angle, and this is what we call the imaginary part of this complex number, of this complex phasor. And so now I've already also almost solved the last task here. This phasor is to be drawn in the complex plane. So I will use the same complex plane as there and just use red. So yeah, and no, maybe I will draw a new one because otherwise it will be too confusing. So this is the real axis, this is the imaginary, this is the real axis, this is the imaginary axis, and then the complex phasor is with 60 degrees and a length of 5 centimeters is maybe looking like this. So this is our voltage. This length here is 5 volt. This angle is 60 degrees. And so then this here is 4.33. And here this position is 2.5. So this is also one nice thing about these phasors, that if you don't know how to calculate cosine and sine functions, you could also just draw it. You take a nice sheet of paper with a grid, and you need to have a ruler and you need to have something to measure angles, but then you can measure an angle of 60 degrees, take a ruler, measure 5 centimeters, for example, and then the horizontal component is the real part, and you should also nicely get to 2.5 centimeters or 2.5 volts in this case, and the vertical component should be 4.33, which is the imaginary unit in this, or no, not the imaginary unit, the imaginary part in this case. Okay, so we have, and there's a question.
Yeah, just a question. How does one denote an imaginary number to have a unit?
Yeah, so here we could say this is the imaginary axis also in volt. Okay. No, yeah, it would be better to add this, yeah, to say this is the imaginary part in volt, this is the real part in volt. Okay, so we have taken our time function because we don't want to deal with time functions, we don't want to solve differential equations. We have converted this into this complex phasor. The complex phasor also has the amplitude and the phase, and we can express this phasor in an exponential form and including directly amplitude and phase, and into a Cartesian form including a real part and an imaginary part where we don't really see amplitude and phase anymore. Of course, they are somehow hidden in there. And the thing that combines this exponential form and the Cartesian form is this trigonometric form, because inside this trigonometric form, we see, okay, this multiplied with this is the real part. We still see amplitude and phase, and the amplitude multiplied with this here at the back, this gives us the imaginary part. It still includes amplitude and phase. Okay, so using this Euler identity, we can do conversion, at least in the one direction. How can we convert in the opposite direction? How, if we have real part and imaginary part, how could we calculate back amplitude and phase? Any ideas for this? So if I have the real part, yeah, we need to find the angle. So the angle, or maybe let's better write it like this: the tangents of this angle is the imaginary part of this complex number divided by the real part of this complex number. Okay, so with this equation we can get the angle. How can we get the amplitude? If you look back at the triangle, the amplitude is the hypotenuse of this triangle. The real part is this, the imaginary part is this. The sum of the squares. So if we take the real part of our complex number, square this at the squared imaginary part of our complex number, and then take the square root of this, then we will get the amplitude. And so we can check. So if I go up and call this real part for a second, and if I take the second thing here and call this imaginary part, and if we take the square root of the real part squared plus the imaginary part squared, then we should get 5, and we get 5. And if I take the So let's check arcus tangens. This is this function, and there's also some arcus tangens in degrees. So if we take the arcus tangens in degrees from the imaginary part divided by the real part, we should get 60, and we get 60. So nicely makes sense. Okay. So with this we can do conversion. Conversion in the one direction, conversion in the other direction. Why do we need these different forms?
It's easier to add in the...
Yeah, so because we want to do different mathematical operations, and it's much easier to do multiplication and division in this form, and let's say squaring this phasor and taking the square root of the phasor, something like this. So powers of this phasor, and it's impossible, let's say, or it's not really possible to do sum and difference. So for summation, we need to have the Cartesian form. And so that's why we need to convert between them. At least if you do the calculation by hand. Of course, if you use a calculator to deal with complex numbers, not so many calculators can deal with complex numbers, but if you use a calculator, the calculator won't care. Or MATLAB Octave won't care. So in MATLAB in Octave, you can always you don't need to do this conversion implicitly. You can just use the calculation there. Okay, so let me shortly go back to MATLAB. So we could also insert the complex number that I will now call complex V. As we discussed before, 5 volt times the exponential function of j, or maybe better 1j times 60 degree, and this exponential function wants to have the angle in radians. So maybe let me change the size of my Octave window here. Okay, so this exponential function wants to have the angle in radians. How do I convert degree into radians? Yeah, divide by 180, multiply with p. And so then we get also our complex number there. And so now we have this, what we really want to have. We want to have one number, one variable that includes real part and imaginary part, or amplitude and phase. And usually these tools like MATLAB Octave, they will always show you the number as real and imaginary part. If you want to have the amplitude or the absolute value, the magnitude of this complex number, how can we calculate magnitude or absolute value with abs? So, yeah, so but there's a function that does this for us. So absolute value. And how do we get the angle? There's a function that is called angle. And this angle, of course, gives us the angle in radians. I think there's also some angle d. No, there's not some angle d, but okay. So let's check if we have phase also. Phase, I think, works in MATLAB, but not in Octave. So, but if we take angle and now multiply with 180, or let's say maybe divide by p first, then we have, yeah, and then, okay. Yeah, so then we get back 60. And this, the arcus tangens function that we used before, this of course also works in this case, but the arcus tangens function has a problem if we have a complex number, if we would have a complex number that has a negative real part. So just a short quick check, if I take an angle that is larger than 90 degree, maybe 120 degree, so then we get a negative real part. So now if I would calculate here our imaginary part again, or maybe I should have taken it just like this. So real part with 120 degree, imaginary part with 120 degree, or real and imaginary part recalculated. So now our arcus tangens in degree formula should give us usually, what should we get? 120, right? But does not work. We get minus 60. And to this minus 60, to this wrong value, we would need to add 180, then we would get the real value. So why do we get the wrong value? Yeah, because with 120 degree, the phasor would be somehow here. And so we have a negative real part and a positive imaginary part. So the quotient of the two, or this fraction, will also be negative. And the arcus tangens function only has some value range of minus 90 degrees to plus 90 degrees. So it will calculate us the wrong number in the opposite quadrant of this complex plane. And so for this case, it's much better to use this angle function, because this is more robust. Or to solve this problem, I mean, the people who develop MATLAB and Octave are also, of course, not stupid. So they have thought of a second function, and it is called arcus tangens 2. And the arcus tangens 2 gets two values. The vertical value and the horizontal value, or let's say in our case the imaginary part and the real part. And then it automatically does the decision, okay, the real part is negative, so I need to add 180 or subtract 180 and so on. So if we use, instead of this function, which gives us the wrong value, where we would need to add 180 to get the right value. So if we use arcus tangens 2 from the imaginary part, not divided by the real part, but imaginary part and real part given separately, and then we need, so this will give us the result in radians. So we need to multiply with 180, divide by p, and we will also get the right value. Yeah, so this is if you manually do conversion. But usually, if you have Octave, if you have MATLAB, if you have something like this, you can just insert complex numbers like I did here. You have some amplitude, you have some phase. You just need to care about the conversion between degree and radians. And if you want to have, and of course you can also, we could also say our complex phasor is 2.5 plus 4.33j, and so then it will also work. And so the real part you always get with real, and the imaginary part you get with this, and the absolute value we already discussed. You get with absolute value, and the phase you get with the angle. And the angle will be given in radians, so you might want to convert to p. And because now I've not given this super exact, the angle is not 60, but just 59.999 anymore. Okay. Question still there? Okay, so then one last thing that we can discuss here in this task is that usually for most of the conversions or for most of the calculations, we would not use these peak phasors here. So this would be a peak phasor, because as we said, this is the peak value. But we would use so-called RMS phasors, root mean square value phasors. And for these RMS phasors, we would use a capital letter maybe I need to write here so that I have more space. So this is now a large V. And yeah, maybe I just write one quick conversion. The RMS phasor is just the peak phasor divided by square root of 2. So whatever you have here, you divide by square root of 2, and then you get this RMS phasor. Now the question, of course, that you might ask, what do we need this RMS phasor for?
Like the effective value?
Yeah, it's the effective value, and what do we need this effective value for? For power calculation. So as long as you just calculate currents and voltage in a circuit, you're totally fine with this peak phasors. If you also care about energy and power, and if you would do measurements in a real circuit, right, with the multimeter that I've shown you, unfortunately I don't have it with me today, but on top of the multimeter you can check some of the recordings of the old exercises. There's something that says true RMS, so it's what the multimeter measures is the RMS value of some current or voltage. And so, of course, if you want to compare a measurement with your calculation, you need to compare with the RMS value and the RMS phasor. And the difference is also important if you calculate power, because if you calculate complex power, maybe I can write this down here. So if we would calculate complex power is usually denoted by S. And if you have RMS phasors, you take voltage phasor multiplied with the current phasor, and you need to have the complex conjugate of this. We can discuss also in a second what complex conjugate means. And yeah, so now if you insert for this RMS phasor this equation, and if you would insert for this RMS phasor this equation, then you can also, of course, calculate complex power from the peak phasors using this equation, because the square root of 2 multiplied with the square root of 2 will turn into a 1 over 2. So also for you can also calculate power from these peak phasors, but then you have to take care about this additional factor of 1 over 2 in this equation. Okay, and so the last thing is, what does complex conjugate means? The imaginary part has the opposite thing. So if we have, yeah, so if in our case, let's say if we would write V complex conjugate, then it would mean it's 2.5 volts minus J 4.33 volt, or it would mean it's 5 volt multiplied with E2 minus J 60 degree. So the imaginary part or the argument or the phase angle have the opposite sign as before.